Can we achieve spatial robustness from only 3 demos? While VLAs and multitask policies offer strong base models, they are not quite able to solve tasks in a true zero-shot manner. Rather, they must be fine-tuned on tens or hundreds of expert demonstrations to achieve success. This is unacceptable if we want robots that can adapt with minimal human effort. Taking the naive approach of training a policy on the few demonstrations given, we show why future imitation learning is challenging. With limited access to data, the policy lacks spatial robustness as the training data only contains a small number of object locations. Moving the target object around during test time, the policy successfully replays the training demonstrations, but fails to generalize to unseen object locations. Leveraging the fact that the community is collecting vast amounts of robot data, we propose STRAP, a retrieval-based policy learning scheme that achieves robustness from few demonstrations. By doing so, STRAP outperforms previous retrieval and behavior cloning methods by up to 43% in multiple real-world scenarios. Our key insights are threefold. First, vision foundation models offer powerful out-of-the-box representations for trajectory retrieval. They sufficiently encode scene semantics and offer visual robustness in contrast to brittle in-domain feature extractors from prior work. We use those models to encode robotic trajectories from our online and offline dataset into a shared latent space. Second, we observe that most demonstrations consist of multiple steps or even tasks. To that end, we propose to retrieve sub-trajectories. This ensures maximal reusability of prior data over retrieving full trajectories. Sub-trajectories further capture the temporality of tasks and dynamics, a feature that is lost when retrieving single time steps. Third, we propose subsequence dynamic time warping to find optimal sub-trajectory matches in the offline dataset. Dynamic time warping is agnostic to the length, horizon, and demonstration frequency, making it a perfect candidate for matching robotic trajectories. As a final step, we train a transformer-based policy on the few demonstrations and the retrieved sub-trajectories. The resulting policy showcases robustness to spatial positions, unseen in the few demonstrations. We showcase STRAP's performance on various real-world kitchen scenes, where it outperforms behavior cloning in zero-shot as well as fine-tuned multitask policies. With increasing size of the offline dataset, here done by adding 50,000 demonstrations from Droid, the gap becomes even more distinctive, as the baselines struggle to learn from the huge offline dataset. Finally, we run a retrieval algorithm on a subset of the Droid dataset. Prompted by a pen and cup demonstration collected in our lab, STRAP finds trajectories in the offline dataset that match the task and the environment of the seed demonstration. Note that even though the seed environment is not part of Droid, STRAP retrieves data from lab setups with astonishing similarity. Let me now leave you with a short summary. We present STRAP, a retrieval-based algorithm that uses foundation model-driven relevance metrics to retrieve sub-trajectories from large offline robotic datasets. STRAP employs subsequence dynamic time warping to find the best matches while being agnostic to horizon and demonstration frequency. These contributions enable STRAP to achieve spatial robustness from as few as 3 demonstrations. Finally, I want to thank my collaborators. Check out our website for more videos and visit our poster session. Thank you for your attention.